So in today's video we're going to look at the differentiation of exponential functions, specifically exponential functions with a base of e, but I will address what would happen if the base wasn't e later on in the video. So those of you following along on the notes, your notes say the graph of y equals e to the power of x is shown opposite, and then you don't have a graph of e to the power of x drawn there, so my apologies for that. But hopefully we all know what the graph of y equals e to the power of x looks like. So a simple exponential function, y-intercept at 1, continuously increasing. So what we want to think about is a fairly informal approach to thinking about, well, what might the derivative of e to the power of x look like? And then I will talk you through a proof. Again, you don't need to be able to replicate the proof in any way, but just a sense of, that we're not just making up rules out of nowhere. Okay, so if we think about the graph of an exponential function, this is y equals e to the power of x. The one thing that we know is, and I said it just previously, that this is an increasing function, a constantly increasing function, and so therefore we know that gradient's always positive for an exponential function. So remember, when we're sketching the graph of a gradient function, we're essentially now imagining that the y-axis becomes gradient, okay? So we know that we're going to have always positive gradient, so we know that our derivative graph is always going to sit above the x-axis, okay? So when x is very, very small, or a very, very negative number, we know that the gradient is going to be a very, very small positive value. So back here we have very, very small positive gradient, whereas up here we have very, very big negative gradient. Okay, so there's a general sense that our gradient graph is going to be going from a very, very small value up to a very, very big value, but probably quicker than that. The gradient is also increasing exponentially. It has a small positive gradient, increasing slightly, increasing slightly, increasing slightly, and then all of a sudden starts to increase rapidly. So remember, gradient, we're thinking about being able to draw a tangent at that point. Actually, if we were to draw a tangent at the point x equals 0, the gradient of that line is 1, and so the gradient of the exponential function at that point is 1, and so therefore it will go through the same point. And in fact, the exponential function y equals e to the power of x is particularly unique, and that's why one of the reasons why we tend to favour a base of e both with logs and exponentials is because the value of the gradient of the curve is equal to the y value of the curve at that point. So when x equals 0, the y value is 1, the gradient is also 1. So when we draw the gradient function, it's going to go through the same point. When x equals 1, the gradient, the y value is e to the 1, and the gradient is also e to the 1. So it's going to go through that same point. Sorry, it's going to go through that same point, etc. Okay? And so actually, the graph of the gradient function, e to the power of x, will certainly also be an exponential function. And in fact, if it is e to the power of x, the graph of the gradient function is also e to the power of x. So the derivative of e to the power of x, we can speculate, looks like it might also be e to the power of x. And it is. And let's have a quick look through the proof. So again, let's think about derivative from first principles. So if f of x is e to the x, f of x plus h is e to the x plus h. So our derivative by first principles, f of x plus h minus f of x all over h, taking the limit as h approaches 0. Okay, and then we're going to work on this expression. So we can split up this term. We know that we add powers when we are multiplying. So e to the power of x times e to the power of h is e to the power of x plus h. So I'm going to write that as a multiplication. This dot means multiplication. It's really commonly used in Europe. And then I've got this common factor of e to the power of x, so I can factor that out, and we now have e to the x times e to the h minus 1 all over h, and then I can split this fraction into two separate fractions, e to the x over h times e to the h minus 1 all over h, and then we can split into two limits, so we can take the limit of e to the x and the limit of that as h approaches 0. Okay, so now the limit of e to the x as h approaches 0, e to the x doesn't have any h's in it, so that's just going to be e to the x, okay? This bit is the more complicated bit, which is addressed over here on the side in blue text. So the graph opposite shows y equals e to the power of x, it's a black line. the tangent is drawn at 0, 1, and it has equation y equals x plus 1. If we think about the graph, we can see that e to the power of x is always bigger than or equal to x plus 1. Okay, that inequality, we can see that that thing is always higher up than that thing. So therefore, e to the power of x is always bigger than or equal to x plus 1. And so we can get this statement here. And then if we were to reflect both these graphs in the y-axis, so if we reflect that graph in the y-axis, that equation becomes e to the negative x. If we reflect the linear graph in the y-axis, that equation becomes negative x plus 1. Okay. We can also therefore see that e to the negative x is always bigger than or equal to negative x plus 1. Okay. And e to the negative x means 1 on e to the x, and negative x plus 1 we can write as 1 minus x. And then we can take the reciprocal of both sides, flipping our inequality as we do that, and that tells us that e to the x is less than or equal to 1 over 1 minus x. Now if we combine together these two red inequalities, okay, these two here, we know that e to the x is bigger than or equal to that thing, but smaller than or equal to that thing. We can create this one inequality that gives us limits for e to the power of x. E to the power of x is bigger than or equal to x plus 1, but less than or equal to 1 over 1 minus x. And then if we do some rearranging of that inequality, so here we are just subtracting 1 from every side of the inequality. Okay, and then all we've done from here to here is just get a common denominator to get that together. And then what we're doing from here to here is dividing each side of the inequality by x. And then what we can do at this point is we'll take the limit as x approaches 0 of each of those inequalities, okay? Of each of those, sides of the inequality. And when we do that, the limit as x approaches 0 of 1 is just 1, fine. The limit as x approaches 0 of this fraction, well, that would become 0, and that's also just 1. And so therefore, if this limit sits in between two things that are both 1, it also has to equal 1. So the limit as x approaches 0 of e to the x minus 1 over x is 1, okay? And therefore we can simply just change the variable, to h's, and we have that the limit as h approaches 0 of e to the h minus 1 over h is in fact 1, okay? And so this thing up here equals 1, and so then this whole thing is just equal to e to the power of x. So derivative by first principles of e to the power of x shows us that the derivative of e to the x is e to the x, okay? So again, you don't need to be able to replicate that proof at all, but you should really be able to follow the logic of that. Okay, so now that we know that if y equals e to the power of x, dy dx equals e to the power of x, then we can use the chain rule to establish some variations on this. Okay, and I'm going to do this the long way around by letting u equal, because I think otherwise it becomes hard for you to see what's actually happening. So if we think about this as a chain rule, a composite function, in that we've substituted a linear function, ax, into an exponential function, e to the x. So I'm going to start by letting u equal ax, okay, which means that y is now equal to e to the u. So then we can differentiate each of these separate expressions. The first one tells us that du dx is just a, and the second one tells us that dy du is e to the u. That's exactly this rule up here. Okay. And we introduced u, so that is e to the ax. And so therefore we know that dy dx is equal to, using our chain rule, dy du times du dx, which means that it is e to the ax multiplied by a. And so we get a e to the ax. So if y equals e to the ax, dy dx is a e to the ax. We can follow the same logic if the inside function is ax plus b. Okay, and again, you can follow through with letting u equal ax plus b. I might see if we can manage to do this one using our shortcut chain rule. So just thinking about covering over the inside function. So I have e to the power of something. The derivative of e to the power of something is still e to the power of something. But then we also need to multiply by the derivative of that something, the derivative of the thing that we shaded, which is a. So we get a e to the ax plus b. And then we could obviously generalize that even further. Any chain rule, e to the power of a function. So a composite function, you've got f of x substituted into e to the power of x. So again, we could let u equal f of x and go through the long process. We could try and shortcut it and just think about, all right, I've got e to the power of something. The derivative of that using my chain rule is e to the power of something. But then we need to multiply by the derivative of that something, which is f dash x. So generally speaking, if y is e to the power of f of x, then dy dx will be f dash x times e to the power of f of x. Okay, let's see if we can work through some examples. So all of our properties of derivatives hold. If we've got products and quotients, we either need to simplify or use the product or quotient rules, etc., etc. Okay, so y equals e to the 5x plus x to the power of 5. So we're adding those two terms. We can just differentiate each of them separately. E to the 5x, the derivative of that, using the rule we just established on the previous page, is 5e to the 5x. You can think about that as a chain rule. You've got e to the power of something. It's e to the power of something, so that's this bit. But then you need to multiply by the derivative of that something, so derivative of 5x, which is 5, which is where the 5 comes from out the front. Okay? And then derivative of x to the power of 5 is 5x to the 4. Okay, so the challenge a number of students have here is they like to try and subtract 1 from this power up here, okay, remembering this is different, this is an exponential function, it's a completely different rule to the polynomials where we bring the number down and we subtract 1 from the power. Subtracting 1 from this power wouldn't make it 4x, it would make it 5x minus 1. But that's not the pattern we follow for exponentials. You've seen the proof of how we differentiate e to the power of x to get e to the power of x, and then applying the chain rule to that means that the derivative of e to the power of 5x would be 5e to the 5x. Okay. Alright, so there's our derivative. Alright, part B, we've got 2 times. Okay, so remember numbers out the front, they don't change the derivative, so we can just think about this as being the derivative of this is being 2 times whatever the derivative of e to the 3x plus 4 is. And again, thinking about your chain rule, so e to the 3x plus 4, derivative of that is still going to be e to the 3x plus 4, and then we have to multiply by the derivative of 3x plus 4, which is 3. So you get 3e to the 3x plus 4. And then obviously we can multiply that together with the 2, you can do that all in one step, so 6 times 3x plus 6 times e to the power of 3x plus 4. Okay, why? We've got a chain rule. So again, you're thinking about e to the power of this quadratic. Okay, so e to the power of something, derivative of e to the power of something, sorry, I'm saying e, I'm trying to write x, is still e to the power of something, so it'll be e to the power of 5x squared plus 3x minus 4, but then we need to multiply by derivative of that something, so derivative of 5x squared plus 3x minus 4, which will be 10x minus, plus 3. Now remember, if there's no brackets around this, this isn't correct. Okay, you're multiplying by all of that derivative, it must have brackets, it says something different if there isn't brackets. We would probably write that as 10x plus 3 times e to the power of 5x squared plus 3x minus 4, but it's not incorrect to leave it at that first line. Okay, so second one, we actually have a chain rule within a chain rule because we have a quadratic function inside a square root function that is inside an exponential function. Okay, so we really just need to take this one step at a time. If you need to let u equal square root of x squared plus 1 and do that derivative separately, then I would encourage that, but it should be possible to do this without needing to do that. So let's focus on the fact that we've got, well actually before I do that, I might just rewrite this as e to the power of x squared plus 1 to the power of a half. Okay. Alright, so then let's focus on covering up our inside function. So we've just got e to the power of something. Okay. So the derivative of e to the power of something is still e to the power of that same something. And then we need to multiply by the derivative of that, which requires the chain rule. Okay, so chain rule. So again, this time now you're thinking about covering up your inside of that. So you've got something to the power of a half, and so that's going to be half times something to the power of negative a half, and then you'll need to multiply by the derivative of that something. So derivative of x squared plus 1, which is 2x. Okay, so again, tidying things up, this is e to the power of square root of x squared plus 1. Half times 2, they cancel each other out. So we've just got x and then the bracket to the power of negative a half, so I might write that as x over square root of x squared plus 1. Okay, you can probably just leave it written that way. You could put your e to the power up onto the fraction if you want. You could write this in a number of different ways. Don't muck around with it too much. Generally speaking, the more steps you do, the more likely you are to make mistakes, so just be careful about kind of not overdoing it too much. Okay, part E, we've got a quotient of two functions, two exponential functions. However, we should be able to simplify this function so that we don't need to use the quotient rule. If we break this up into three separate fractions, okay, this is the same as having 4e to the 3x over e to the x plus e to the x over e to the x minus 3 over e to the x. Okay, so index laws, we subtract powers when we're dividing, so that's going to be 4e to the 2x, e to the x divided by e to the x, that's just 1, and this will be 3e to the negative x. Okay, so now we're in a position to differentiate it, and we don't need product or quotient rule here. dy dx is going to be, so we bring down that 2, becomes 8e, but it's still 2x when it's an exponential. Derivative of 1 is 0, so we can ignore that. Again, bringing down the negative 1 as the coefficient of x in the power. And so again, that's about the chain rule. So you're thinking about covering up, you've got e to the something, derivative of that is e to the something, and then you divide by the derivative of negative x, which is negative 1. Okay, sorry, multiply by the derivative of negative x, which is negative 1, which is how we're going to get plus 3. So it's bringing that negative 1 down the front. So we get plus 3e, and the power doesn't change when we're differentiating an exponential function. Again, I would stop here. Okay, if you really want to, if you're trying to get it, if the question is to show that it looks like something, yes, we could write this back as 3 over e to the x, and yes, we could get a common denominator by saying it's 8e to the 3x plus 3 all over e to the x, but there is nothing wrong with that top line, and you can stop at that point. Okay, part F, we've got x squared times e to the negative 3x, so we have a product. X squared, a quadratic, multiplied by e to the negative 3x, an exponential. Okay, so we're going to need to use our product rule here. dy dx. Now product rule, we differentiate the first function, so that's x squared, derivative of that is 2x, and we leave the second function as it is, e to the negative 3x. We add for the product rule, we leave the first function as it is, and we differentiate the second function, which will give us negative 3 e to the negative 3x. Okay, so tidying all that up, we've got 2x e to the negative 3x minus 3x squared e to the negative 3x. Now when you do product rule with an exponential function, because of the way you differentiate exponentials, you'll always find that you get that common factor. So actually, if we think about factoring out e to the negative 3x, we're going to be left with 2x minus 3x squared. And actually, in terms of fully factorising, you might actually take out that x. So you might write it as x, it's going to be 2 minus 3x, and then e to the negative 3x. And again, if you're trying to solve the derivative equal to 0, you need to factorise it to be able to solve it. And so whilst you've answered the question at this point up here, this point down here is often something that's easier to work with. Okay, so being able to make those steps is key. Alright, and then part G here, we've got a quotient of two functions. Now we can't break up this function to simplify it. Okay, it might be tempting to say, oh, but that's not how fractions work. Okay, if you've got x plus, or if you've got a plus b over 2, that's the same as a over 2 plus b over 2. Okay, but it's not the same as, sorry, if you've got 2 over a plus b, that's not the same as 2 over a plus 2 over b. Okay, because going back this way would require a common denominator, which would mean you get 2b plus 2a over ab, which is not that. Okay, so you can't just break up the denominator of a fraction. You can break up a fraction by splitting up the numerator all over the same denominator, but you can't do it the other way. So this one can't be simplified in any way, and so therefore we're going to be forced to use the quotient rule. We've got a quotient of two exponential functions. So quotient rule, dy dx. Quotient rule, we differentiate the numerator, so derivative of e to the x is still e to the x, and we leave the denominator as it is. We then subtract in the quotient rule. We leave the numerator as it is, and we then differentiate the denominator. So e to the 2x will become 2e to the 2x, and derivative of 1 is 0. And then the denominator is squared with the quotient rule. Okay, let's just tidy up the numerator. So we're going to have, let's expand out the bracket. So e to the x times e to the 2x is e to the 3x plus e to the x. And then e to the x times 2e to the 2x, so we're going to get minus 2e to the 3x over e to the 2x plus 1 all squared. Okay, so that is e to the x minus e to the 3x, so just collecting together those like terms, over e to the 2x plus 1 all squared. Okay, that's probably fine as it is. You might choose to factor out e to the x on the numerator, but there's not really anything else you can do with that. I certainly wouldn't bother expanding out the denominator. There's no reason to do that. In fact, factorised denominator allows you to see whether there's any common factors that will cancel down, so there's no reason to expand it out. Okay, example 2. Find f dash at -1 if f of x is equal to this particular function here. Okay, so we need to find f dash x first, and then we want to substitute -1 into that. Okay, so we've got a couple of things going on here. We've got a product of a quadratic function and an exponential function, but then this exponential function is also going to require the chain rule. So we're going to need product and chain to differentiate this. Okay, so f dash x, product rule first of all, we're going to think about derivative of the first function, which will be 2x plus 2. Leave the second function as it is, plus we leave the first function as it is, and we differentiate the second function. Now the derivative of the second function is going to require the chain rule. So again, thinking about, cover up your inside function. You've got e to the power of something. E to the power of something is derivative of e to the power of something is still e to the power of something, but then you need to multiply by the derivative of that something, so that bit I've shaded in grey, so that is negative 2x. Okay, so let's see what we've got here. We have got, I might factor out the 2 in that bracket, so I'm going to have 2 times x plus 1, e to the 3 minus x squared, plus, now there's a common factor of x here, let's put that together with the negative 2, sorry, so it's actually going to be minus, isn't it? Minus 2, now there's the x here, and I'm also going to take an x out of that bracket, so there'll be x squared, and then there's just x plus 2 left in the bracket, and then we have e to the 3 minus x squared. Now once again, okay, you've differentiated, you can stop at this point, but you'll always find that you've got the e, the term with the e in it is common, so you could always take that out as a common factor, and in this instance we could also take out the 2 as a common factor. So if we take out 2e to the 3 minus x squared, we're going to be left with x plus 1, take away x squared x times x plus 2. So let's expand out the bracket and collect some like terms and see what we've got. So we're going to have x plus 1 minus x cubed minus 2x. Okay, so, and I'm just going to write that bracket in front of the exponential, just because conventionally that's how we usually see them. So we're going to have 1 x minus 2x is minus x cubed, and we've got that times e to the power of 3 minus x squared. Okay, so again, you have differentiated at this point, but if you then want to maybe solve equal to 0, this is going to be a much nicer place from which to do that. And again, if the question says, find the derivative of this in the following form, then you're going to need to be able to make that manipulation. Okay, example 3, the final example here. This is where I want to have a look at. Okay, what about if you want to try and differentiate an exponential that doesn't have a base of e? And we're just going to, you won't be asked to do that, you won't be asked to differentiate 3 to the power of x, but I'm going to show you how it's possible to do that by stepping you through these 2 steps here. So we want to first of all show that 2 to the power of x is equal to e to the power of log e of 2 times x. Okay, so remember, a show that question, we either want to start with this and turn it into this, or we want to start with this and turn it into this. Okay, now it's usually easier to start with the slightly messier looking thing and turn it into the neater looking thing, and that's the option I'm going to take here. So e to the ln 2 times x, so remembering ln is log base e, So if you prefer to write that out to see what's happening, that's okay as well. Alright, so when do we multiply powers? Well, we multiply powers when we have one power being applied after the other power, okay? And so we could rewrite this in that way. So we could say, well, this is the same as e to the log e of 2 all to the power of x. Alright, and then we know that e to the log e, they're inverse operations, they're cancelling each other out. And so inside that bracket, that is just 2. Okay, and so we have 2 to the power of x. Alright, so we've shown that that's true. And so hence, find a derivative of 2 to the power of x. Find the derivative of 2 to the power of x. So hence, meaning you must use part A. Okay? If it says hence or otherwise, it's a hint. You could use part A, but if you want to do it another way, that's okay. But if it says hence, you have to use what you've done in part A. Okay, so if we want to find a derivative of 2 to the power of x, well, we don't know how to do that. But if we think about 2 to the power of x as being the same as, so derivative of 2 to the power of x, well, 2 to the power of x is the same as, we've just shown, e to the log e of 2 times x. Okay? And so, remembering, this is just a number. That's just a number. It's just e to the ax. And derivative of e to the ax is a e to the ax. And so the derivative of 2 to the power of x is log e of 2 times e to the log e of 2 times x. Okay. And that would be obviously true. We could extend that to any exponential with another base. If we had log e of a, sorry, derivative of a to the power of x, well, a to the power of x could be written as e to the log e of a times x, and so therefore the derivative would be log e of a times e to the log e of a times x. Okay. So that would be generally true. You're not going to be expected to know that rule in particular, but you should be able to work through a question that sort of steps you through the process that you would need. So if I ask you to show that this is equal to this, and then hence differentiate that, then as long as you're sort of stepped through it, you should be able to do that. Okay, once again, the work today is from a worksheet. The worksheet can be found printed in Appendix F of your blue booklet.